Hello and welcome to Physics 2212 Lab 3, Electric Circuits. The purpose of this lab was to see how resistors, capacitors, and batteries interact with one another in a circuit. We used voltmeters and ammeters to compare real-world measurements with the results from a digital model. Starting with some key principles, Kirchhoff's voltage law states that the sum of the voltages across a loop is equal to zero, which is a consequence of the conservation of energy. Kirchhoff's current law states that the current entering a node is equal to the current exiting a node. This is a consequence of the conservation of charge. Then there is Ohm's law, which states that the voltage across a circuit element is given by the resistance multiplied by the current. For a brief preview of the results, it was found that Kirchhoff's voltage law holds true and that the sum of the voltages in a loop must add to zero. The second result was that increasing the resistance in an RC circuit increases the charging and discharging time for the capacitor. The following series circuit was set up as follows. Here there is a 47 ohm and a 100 ohm resistor in series with one another, connected to two batteries each, which both have 1.5 volts each. Using Ohm's law, we calculate the current at I1 and I2 to be 20.4 milliamps. This is exactly what we measured using the ammeter as shown in the image on the right. When one of the ammeters was replaced by a voltmeter connected in the same way, the voltmeter read 3 volts, whilst the ammeter was reading 0 current. This is because there is a total potential drop of 3 volts across the entire circuit. Voltmeters also have extremely high resistance, which results in extremely insignificant current within the circuit as demonstrated using Ohm's law. When the voltages were all summed up, you get a total of 2.9 volts, where it should theoretically be 3 volts according to Kirchhoff's voltage law. We measured the potential differences across all the circuit elements with the values displayed here. We approximated the potential drop across the ammeter and wires to be essentially 0 volts when completing the graph, which is shown on the right for simplicity. Here the gradient for the 47 ohm resistor is not as steep as that for the 100 ohm resistor. This is because there is a smaller potential drop across the 47 ohm resistor. Using the previously measured values for the potential drop, we were then able to calculate the actual resistance for each of the following circuit elements using Ohm's law, which can be arranged to give R equals V divided by I. Our calculated values are shown here. When an ammeter was placed in parallel to the 100 ohm resistor, the current measured by the other ammeter increased to 53.6 milliamps. This is because the ammeter has a very small resistance. This decreases the overall resistance of the resistor combination and leads to more current being drawn from the battery. For the RC circuit, we set it up according to the diagram on the right. Our actual setup is shown in the picture here. For the charging process, we measured the time it took for the light bulb to dim when it was connected to a battery. For the discharging process, the battery was disconnected, leaving only the capacitor and light bulb. Again, the time taken for the light bulb to dim was measured for the discharge time. Here we measured the charging and discharge times for the 10 ohm resistor to be around 16 seconds, whilst the time for the 20 ohm resistor was roughly 30 seconds. This means that the greater the resistance, the less current that flows. This means it takes longer for the capacitor to become fully charged or discharged. The model results are shown here. We used the equation shown on the right. The natural log of both sides was taken to give the linearized model, where -1 on RC is the gradient. The RC calculations are shown here. When this is all plotted on a graph, we see that the 10 ohm resistor's log of the voltage decreasing twice as fast as that of the 20 ohm resistor, which agrees with our experimental results. Both the ideal model and physical experiment gave similar results. However, possible sources of error include human error from the visual observation of the light bulbs, charging and discharging. This random error could be mitigated by taking more time measurements to ensure precise and accurate results. If we charged a capacitor with no resistor in the circuit, Kirchhoff's voltage law would predict that the capacitor should charge instantly and that there will instantly be a potential difference of 3 volts across the capacitor. This would not happen in real life, as the wires themselves would have some amount of resistance, meaning that the amount of time to charge the capacitor is non-zero.